Okay, so here is my talk. First of all, I would like to thank the organizers very much. It's a beautiful place here, and even though I'm from New Zealand, I sort of feel familiar around these parts. Now, wondering which one works. The other one, maybe better. Okay, so I'm going to continue to talk about solitons and solitary waves. Now this, of course, was a wonderful introduction that was already given previously. Just want to point out that, of course, solitary waves are well known in many systems in physics. So here is one in water. You know, this is a wave on a calm day on the ocean in a protected area of water, of shallow water. That's moving towards the beach, and you've already seen this picture flashed, which is related to solitary waves that you can expect in a cylindrically trapped, cylindrically trapped superfluid. Now, a lot of the study of solitary waves or solitons historically has emphasized the overarching properties and the ubiquitous properties of solitons and solitary waves that appear in all sorts of different systems. But I'm quite intrigued by the, okay, now this of course doesn't work if I don't plug it in. So this was a discussion article written by James Anglin on the occasion of observations done in Klaus Engstop's group of dark solitons in the Bose-Einstein condensate. So asking the question of, canaries, you send canaries in a gold mine, in a coal mine usually to detect gases, to detect things that are otherwise difficult to measure. So can solitons be used to measure some interesting properties of a gas, of a superfluid, of a system fluid in general, I would say. And of course, then the idea is these solitons probe the fluid at a length scale which is much smaller than other probes that you have, or is, it's sort of a unique length scale, intermediate length scale, mesoscopic length scale between the completely atomic length scale and then the macroscopic length scales of sound waves. Okay, so this is sort of an overarching question that I'm interested in. And here I'm just showing some pictures, observations that were done in this experiment of Engstop's group, where they saw solitons moving back and forth in a harmonically trapped background. And if you solve the Gross-Petersky equation, nonlinear Schrödinger equation in just 1D, numerically you see exactly that something like this is happening. They're going back and forth, and then you can ask about the question of the frequency of these oscillations. And the frequency of these oscillations is related to the trap frequency in a way that the square of that from the Gross-Petersky equation comes out to be 2. Okay, in a regime where you have fairly strong nonlinearity, where you have a big system. Okay, and so this can be related to the ratio of the mass, the inertial mass, to the physical mass. So the physical mass is some kind of buoyancy mass, and I will go into that a little bit. So this is the prediction from Gross-Petersky theory, and it worked out beautifully in Bose-Einstein condensates.
Excuse me, I have a quick question.
Sure.
In relation to this, so I know how it works technically, this spectral fluid, but is there any intuition why it's exactly the spectral fluid? Is there any way to understand why it's fluid?
I'll get to that. Yeah, I'm not sure I can fully answer your question, but I will attempt to. I will show you some indication. Two slides.
In many cases, can be anything. Right? So it seems like there's no magic number, the irrational masses in the DCS. Yes. I will exactly talk about this, the magic in this ratio. Right. So it is a little bit. It's still magic for me. Let's say, it is still magic. So then, so here is is data from an experiment that was done by Martin in his lab in a Fermi gas, and so they imprinted first solitons, but then they had decayed into vortices, and then these vortices
had very large mass ratios. Okay, so here's the oscillation frequency, and this is the mass ratio, which is the square of that number, can become pretty large. So this is what was observed for the vortices. Now, a theory prediction that we were involved in earlier had predicted a ratio of 3, okay, which is, and 2, or here square root of 2, that was the Gross-Pitevsky prediction. Now, okay, I'll tell you a little bit about what this means and how, at least how technically you can get there, or how you can understand where it comes from. Let's first of all go through that a little bit. So the basic idea behind it comes from understanding the soliton as a quasiparticle, basically in the sense of Landau quasiparticle theory. And so Lev Pitayevsky has put this idea forward in a number of very inspiring papers. So the idea is that, you know, if a soliton moves in a slowly changing environment, then its dynamics can be predicted basically from knowing its dispersion relation. So this is knowing its properties that it has in a homogeneous gas. Okay, and the effective mass is particularly helpful. So how does this dispersion relation work? Dispersion relation gives you the energy of the soliton as an excitation compared to the background. You know, which it's just basically the grand canonical energy minus some background energy. Okay, so, and that is a function of a number of parameters. So chemical potential here characterizes the background. Then you have one parameter that actually characterizes the nature of the soliton, which is the velocity. And I put in G here as an interaction constant to characterize, again, the nature of the background. So you, in the BEC-BCS crossover, you would tune G. Okay, so then you can introduce a canonical momentum basically by requiring this relation, that the derivative of the energy with respect to the momentum is a velocity. And then you can draw curves like that, where you, so basically this reparameterizes, instead of the velocity, you can plot it as a function of momentum, and you get something like this. So this looks like an upside down parabola. It's not strictly a parabola, but looks pretty close to it. And that allows us to define an effective mass, just basically from this relation. This is the inertial mass, and it will be negative because it's an upside down parabola. So these are whole quasiparticles in that sense. So the inertial mass gives this response here to basically change of the velocity. And then the heavy mass tells you essentially, or the physical mass tells you, is a kind of buoyancy, is related to buoyancy phenomena. Yeah, so it tells you, well, it basically incorporates how many particles are missing from the density here at the place where the soliton is, where the number of particles in the soliton here is, yeah, that's just an integral over the density here. Now, again, this can be obtained from the dispersion relation, from knowing this energy. So it's actually fairly beautiful. Just by knowing this and then taking some derivatives, you can calculate all these properties. And then the logic of this quasi-particle dynamics is very simple. Essentially, it says, you know, if you have a superfluid, in this case, a fluid in a background that is changing in space, and your soliton moves, you know, fairly slowly adiabatically with a velocity, you can say, well, the total energy should be conserved around that. So you take the total derivative with respect to time, where, you know, you have to take a derivative with respect to z, and then z time and the velocity, and you get out an equation that looks like Newton's equation of motion, and you obtain small amplitude oscillations, and you can derive this this relation. So the frequency ratio square is given by the ratio of these effective mass parameters. And for solitons, I already told you for the Gross-Pitevsky equation, already told you this is 2.
In this approximation, it means that E0 is constant.
It means that ES is constant, yes. ES, and ES is this energy of the soliton above the background.
This point E0 that corresponds to it.
Oh, sorry. No. This was E0 here is just the first point. This is the energy at zero velocity essentially, and then
that would also depend on the density of your background.
That still depends on the density or on the chemical potential here.
This has to be constant for that. You are the derivation to follow.
Oh, yes. In order, yeah. So this derivative is taken with respect to the chemical potential constant. That's right. But this derivative here is taken with respect to velocity constant, where the background changes. Okay, so that will give you the number of particles that is missing from the soliton. So this is actually the zero velocity version of that relation. It looks a little bit more complicated if you do it for finite velocity, but you can still basically by rules of thermodynamic calculus you can get it from this dispersion relation. So it's important that you know both of these dependencies. In order to derive these quasiparticle equations of motion.
Is there a simple picture why the energy decreases as you speed up the soliton? I would have thought that would create some phase twist energy that you can use.
Yes, so there's, okay, when the soliton is at zero velocity, there's already phase twist of pi. Okay, I haven't talked about the phase twist. It's really important for dark solitons. As you go to higher velocity, the phase actually gradually is less twisted. Okay, so you can say, well, that probably costs less energy, and that is true. And the density fills up. So as you go further and further, the phase untwists, the density fills up. Essentially, actually, the length scale of the soliton also increases. Eventually it goes away. So this is what happens when you go down here. Actually, so the slope becomes here the speed of sound. So that means a gray soliton, as it fills up and as the phase untwists, it becomes more and more like a sound wave, and its excitation energy goes to zero. Okay. So now let's move to the Fermi gas, and of course Martin already introduced this picture. It's very useful Feshbach resonance that we have in experiments where we can tune specifically. I want to look at here at this unitary limit where the S-wave scattering length diverges, which is fairly interesting regime. Now the question, and essentially, I mean, this follows up in some sense from Klaus Engstock's question on what is different here in the Fermi gas, and can you see something specific even though you don't have a Gross-Pidevsky equation. So this is exactly one of the questions that we were interested in. Now I want to walk you through a fairly simple argument, and probably several of you, probably Sandro, will tell me why this does not make a lot of sense, but anyway, it is sort of I'm intrigued by it. Okay, so anyway, so let's look at the equation of state for a Bose-Einstein condensate. Says the chemical potential is proportional to the density. Yeah, or I can write it to the density to the 2 over 2, power 2 over 2. For the unitary Fermi gas, the energy here is also proportional. The chemical potential is also proportional to, well, it's proportional to the Fermi energy of the non-interacting gas. So it's proportional to the density to the power 2 over 3. Now I can do the following thought experiment. I think of having a gas trapped in a harmonic potential, okay, which will, according to a local density approximation, will give us a density profile that, I mean, what exactly that looks like comes out of this equation of state. Now, from the equation of state, I can also determine the speed of sound, the local speed of sound. Now, if I think of phonons, let's say a wave packet of phonons traveling at the local speed of sound, and let them travel across this density profile
as they go towards the edge, the speed of sound goes to 0, so they will have to turn around. If I do this, I mean, just formally, I get an equation of motion that again looks like a harmonic oscillator equation. So it's like a wave packet of phonons. If we ignore that it disperses, it would have sinusoidal oscillations back and forth. And then if I look at, so what is the oscillation frequency and the ratio to the trap frequency, square it, I get 2 for the Gross-Bedevsky equation of state. I get 3 for the unitary gas equation of state. Okay, so here comes Victor's question. So is there some magic in this number 2? It looks like there is some magic in that it is the power law exponent in the equation of state. Now, this is something that confuses me a little bit myself, because thinking of solitons being something different from sound waves and probing the gas in a different way, it seems like for sound waves, when I do the calculation, I get exactly the same things that I get for solitons. Well, I still have some slides. I'm showing you that, trying to convince you that for solitons we also get 3, or we should get 3. But okay, so this is general, comes just from the equation of state, and I will actually show you later another example for a one-dimensional Fermi gas, where even for soliton, or what you can call soliton-like excitation, well, in the one-dimensional Fermi gas, this exponent is 1 in the non-interacting Fermi gas, and true in the limit of 1D fermions non-interacting, we get a ratio of 1. Yeah. Okay. So this is phonons in the in the unitary Fermi gas. For solitons, okay, we did some work a while ago. So there was some theory work that we did in New Zealand, and at the same time, the Trento group also did some work, and basically we agreed on the same results. So what we did at that time, we used some analytical arguments that were based on scaling arguments and a few assumptions, and I admit they were unproven, but they seemed somehow reasonable, and they just gave us this number of 3. And okay, we thought that's a nice, interesting result. But this was also backed up then by numerical solutions, so we solved the time-independent Bogoliubov-de Gennes equation to calculate the dispersion relation and do it in the way that I explained before.
So in this scaling argument, the dispersion state, is it a mean-field statement or is it beyond mean field?
So the argument here, that was, well, it was beyond mean field.
Bogoliubov-de Gennes is mean field, so how could they be that?
Well, or let's say, okay, no, the scaling arguments did not, well, the scaling arguments are somehow pieced together. So there's a scaling which is basically just done on dimensional analysis. So it does not rely specifically on mean field theory. It's just dimensional analysis. But then there's a leap of faith where you have to make an assumption that is, that I can't really justify.
I think that the example that you presented about the behavior of phonons,
yes.
So the argument are based on hydrodynamics.
Yes.
And this is not related to the accessible mean field.
Well, okay, so this argument is not specifically based on hydrodynamics. Yes, if you do the hydrodynamics-based argument, if you just do phonons, as I explained before, you get the number 3. So this argument was different. It was not, I mean, it was based on scaling arguments, on basically dimensional analysis, and then assuming that a specific, that you can simplify, write a differential equation in a specific way that just looked obvious. Okay, so, but again, I cannot actually say, why that should be true. But we wrote it down, we got the factor of 3, and we were just happy that it agreed. So I can't say that this is a really good argument. It just, but of course we also, check this with numerical solutions of
mean field theory, and that gave the same number, both from the dispersion relations, looking at the curvature of the dispersion relation. So I mean these, you know, taking these derivatives here from the dispersion relation, and then time-dependent Bogoliubov-de equation solutions were actually performed here by Robin Scott and Trento collaborators. And they all found in the unitary regime, they found this square root of 2 for the ratio of the, square root of 3 for the ratio of the frequencies. Okay, so there is some numerical uncertainty, but I think within the accuracy of that calculations. So this agreed. Yes?
Just to understand the point that you're trying to make, in the difference between the dynamics of the soliton and the sound wave. Your soliton, say, prepare that soliton with new phases, it moves towards the edge of the track, phase unwinds, and it becomes less and less of the soliton and normal sound waves. So somewhere they should be one and the same. Why does it surprise you?
Okay, why does it surprise me? So the arguments that we've used for solitons are basically, or they're based on the dispersion relations, they're solitons with small amplitude oscillations. Okay, so if you have a soliton that's almost has a pi phase difference and you put it in the middle, it will only do very small amplitude oscillations, right? So this is the frequency that you would get from this mass ratio. Now, I've discussed with with some colleagues from nonlinear, from applied math about what happens with the sound wave argument. First of all, sound waves, they would travel completely to the edge of the trap and then back. Now, whenever so could that be just the limit of a soliton that is already pretty weak, or it's already has phases almost unwound? Not quite, because the soliton, whenever it returns, it actually becomes a black soliton, and the phase at the turning point of a soliton, at the turning point it will have a pi phase. That's where its velocity is 0. So whenever you have a soliton, even a fast-moving soliton, and you get it to some part to its turning point, it will become a black soliton. Okay, so for that reason, at least from regular perturbation theory, you cannot really justify replacing solitons by sound waves. Now, in the Gross-Pitevsky equation, at least the oscillation frequency of the soliton is indeed independent of its amplitude. So you can take the limit of having an amplitude that is the whole Thomas Fermi profile. Okay, so I think that's all I can say, and I should probably move on. Okay, so I guess the question is that puzzles me: does the equation of state completely determine the mass ratio of solitons? And if so, why? I don't really see any reason why it should. Okay, it somehow looks like that it does. Okay, now let's move to an example of a one-dimensional Fermi superfluid, which is also interesting because there we can do theory that goes beyond mean field theory. So first of all, I would like to mention what also Martin mentioned earlier, that there was some very beautiful theory by Dimitri Fimkim and Viktor Galitsky, both in the audience, who solved mean field theory. Well, in mean field theory in one dimension, the Bogoliubov-de equation for a dark soliton. Now, the prediction of that theory is quite interesting in terms of what it says about the masses, about the inertial mass and the physical mass, especially when you look at the limit where now the gap goes to 0, so this is the weakly interacting limit, this is the BCS limit. It says that the inertial mass goes to minus infinity, and the physical mass then, okay, so that is maybe not completely clear, but depending on how you argue and justify this one-dimensional equation, you get either positive or negative 0, but in any case, so if you take the ratio, you will have something that diverges. Right? Now, of course, they're not claiming that this one-dimensional theory actually applies to a strongly confined one-dimensional gas. And I'm going to present you with some theory for the strongly confined one-dimensional gas, so it's maybe not surprising to not get the same, but but at least from this mean field prediction, it looks like something, you know, dramatic should happen. The mass, the inertial mass of the soliton in particular, should get infinite if you go into this now weakly interacting BCS limit. Okay, so we're going to solve now the Bethe ansatz equations for the purely one-dimensional Fermi gas in this case. So we have one-dimensional fermions that interact with delta function interactions, attractive delta function interactions. And you can solve this model regardless of whether you have bosons, fermions, and multiple components or anything exactly with the Bethe ansatz. And I would like to draw your attention that there's a poster by Alex Ayet later today on quantum bright solitons in the attractive Bose gas, which are also described by this Hamiltonian. Okay, but now I want to talk about spin 1/2 fermions, same number of up and down particles. This was first solved by Yang and Godin. And it provides a crossover with an interaction dimensionless coupling parameter gamma, which is given by this interaction strength G and divided by the density, essentially. Okay, so you have a crossover and two limits. So in one limit, where gamma becomes 0, you have a free Fermi gas. You still have bound pairs of fermions, but they become now very long range. Okay, so this could be compared to a BCS-like limit where you might hope that BCS theory might be applicable. Okay, and it's been claimed actually in the literature in several cases that that is the case. Now, then there's a different limit where where G is now strongly attractive, so where you have strongly bound pairs, strongly bound dimers. In this case, you get a Tongs-Jurado gas of dimers. So what does that mean? You have dimers that are strongly bound, but the dimer scattering is essentially repulsive. They cannot get past each other. Okay, so they're like hard spheres or hard point particles that cannot get past each other. Okay, and then in between there's a crossover regime. So then, how do we find solitons in this model? So that is a little bit of a of a tricky question, tricky conceptual question. For one point, you can argue there's no condensate, so there should be no phase. So having phase differences, phase offsets like you seem to need for dark solitons is not true. On the other hand, you can find excitation branches that look very much like these dark soliton branches, like these inverted parabola that I showed you before. And there's a whole bunch of arguments that I don't want to go into right now for why we identify these excitation branches with dark solitons. So we also call these excitation branches the Yrast states, which is a nomenclature that comes from nuclear physics, as far as I understand. It's derived from a Swedish word, and that specifically says it's the lowest energy state at a given momentum. Okay, so this is another interesting feature here. So we identify them with dark solitons, but so there is actually, so let's say at momentum here, or angular momentum is it as it was in a ring. So this is actually specifically a spectrum for ring periodic box boundary conditions. At this given momentum, this is the lowest energy excitation that you can make. So there's a regime where you cannot go. You cannot make any excitation that lives in that regime, which also tells you that if you make an excitation here, it's going to live for quite some time, as long as it cannot trade momentum somewhere else. Okay, so specifically, we're just going to look at these excitations now.
In a finite system, there will be some discretization in momentum, and then it looks like this. Now, these points down here, so it's called here an Umklapp excitation, that actually corresponds to a ring current state. So this is where, you know, we're in a ring periodic boundary conditions now. We have a ground state that has 0 momentum, let's say, and basically we can give the whole thing a Galilean boost, give all particles some unit angular momentum, and then it will be in a ring current state, and this is this state. So, but this is in some sense a boring state because it's just a translation of the ground state. The more interesting things that we claim correspond to something like dark solitons are the states in between. Okay, and in the one-dimensional Bose gas, it looks very similar to this attractive spin 1/2 Fermi gas. In the one-dimensional Bose gas, these are known as the type 2 elementary excitations. Okay, so for the Fermi gas, we're solving the Bethe ansatz equations in coordinate Bethe ansatz equations. They look like this. So you have a number of quantum numbers. They're called rapidities. They go by the names of k and alpha. So they're related to charge and spin degrees of freedom. The number of fermions is n is fixed, and the number m of spin up fermions is we fix it to 1/2 of the number of fermions. And then so you have to solve these equations, you know, for a given number of particles, and then you get the momentum just by adding these k quantum numbers, and you get the total energy by adding k squared. Yeah. Okay. Sure. So you can go into a thermodynamic limit and solve them there as Fredholm integral differential equations, and you get dispersion relations that look like this. Okay, so they look very similar to what I showed you before for dark solitons. Now, I also told you that from derivatives of this dispersion relation, once you know it, you can calculate things like the missing particle number and the phase step and momentum and so on. So momentum here in these units goes from 0 to 2. We get a missing particle number that varies between -1 and -2. Okay, so that is maybe not so surprising, because one limit here, weak interactions, we really have a weakly interacting Fermi gas. These are really single fermion holes. You make a hole, take one fermion out, so we get a missing particle number that is -1. Whereas in this other limit, we have strongly bound dimers. So if you want to make a hole there, an Yrast excitation, you have to take out a pair. So you get a missing particle number of -2. Now, what this phase step means is a different question, and maybe I don't want to dwell on it. But it's related to some backflow current. Now, let's get to the interesting result, which is the masses and the mass ratio. So, so here is the mass, and the blue line is the physical mass. So this is the buoyant mass. Showed you that the particle number goes from -1 to -2. So again, in units of the fermion mass, this goes from -2 to -1. But look here at the inertial mass. Inertial mass also goes from -2 to -1. And then if you look at the ratio is 2 in either limit, is 1 in either limit. But in between it has an interesting feature. So here's what I promised you before. You know, this 1 you could have gotten from the equation of state, because in this regime we have a non-interacting Fermi gas. In this regime, we have a Tong-Schur-Dot gas of dimers, which is also equivalent to a non-interacting Fermi gas in sense of its equation of state. So, so yes, we do get 1 in either limit. And there's an interesting regime where now the mass ratio is actually smaller than 1. So what does that mean? It means that soliton, or, well, oscillations of these quasiparticles, even if you don't want to call them solitons, they should be there. Oscillations on a slowly moving oscillations on a background in a trap would go at a frequency which is now higher than the trap frequency. So they're not slower as in the other cases we had before. Okay, now I see that I've run out of time. Yes, that is true. Okay, so I will leave the rest of my outline there of things that you can ask me about later, and I will not. Now, actually, I should probably. Well, how do I go quickly from? Okay, just to the slide where I acknowledge my collaborators and co-workers. So at Massey University, a number of people have worked on this particular, the one-dimensional Fermi gases. Sophie Shamailov has done a lot of good work, and Wen Yuan Liao is some of the older work. And we have very nice and active collaborations with people elsewhere. At Swinburne University, I didn't talk about this, and then the Trento group in particular. All right, thank you.